specimen mounted on a tensile testing machine, and there is a little bit of a initial defect introduced at the center of the specimen. So we loaded for hundreds and thousands of cycles to crack the specimen until it became something like this. And this is the Martelet water sensing unit, and that's the excitation ultrasonic, transmitting ultrasonic transducer or excitation transducer. So that sends the kilohertz, 500 kilohertz solid stress waves into the aluminum plate, and this is the receiving ultrasonic transducer. And the signal is collected by the Martelet wireless unit again. And that's a photo of the cracked specimen. So that's the center initial defect. You can see this very round circle. And this dark area is when it goes back and forth, a lot of heat is generated. That's the fatigue propagation region, and this area is the fast fracture region. And this is a sample signal collected through the ultrasonic excitation and the receiving. And our sampling frequency here is 2.67 megahertz. And you can notice that from the time axis. So it should be μs, which means microsecond. So that is 10 to the power of -6. That's kind of a high-speed data collection we're doing here. And we get the received signal, we calculate the amplitude. We're using a very simple result processing technique here. Just gather the amplitude. So if crack happens or grows, that amplitude value is going to reduce. And that's exactly what we have observed through the test. So every round here you see is 1,000 cycles of fatigue loading. After first round, that's the crack length in inches. Second round, third round, fourth round. Then after a few hundred, the specimen just broke apart. So at every round, the black line is the round one. After the 1,000 cycles, after round one, we stop at different tension levels. So we hold the specimen, we apply a constant tension, then do the ultrasonic excitation. We get the amplitude. So this is round one. And this is round two at different tension levels. So as we can see, when the tension level increases, the crack opens a little bit, then that causes decreased amplitude. Also at the same time, for the different tension level, for example, 3 Ks, from top to bottom, when the crack length grows, the amplitude is also reducing. Those are all as expected. So I'll quickly go through a little bit of wind motion analysis study results that our partners at a lot of this is reviewing what the first presentation had. So this is called MFI method developed by the audience group. And it's based on a finite model of the bridge and measure the bridge response to obtain axle loads to catch overweighted trucks. And it's a case study on this US 78 bridge between Birmingham and Memphis, and they instrumented one side of the bridge. So those are the sensor instrumentation. There's bed sensor for axle detection on the slab, and there's wind sensors at the bottom. So this is the plan layout of the sensor instrumentation. So as seen in the first presentation, they built a high fidelity finite model, and they validated the model using field validation. That's the first natural frequency of the bridge span, etc. So they calibrated the model using field measurements. And those are the wind motion results for a simple 2-axle truck. I believe what you saw earlier was a more complicated 5-axle truck. So using a simple 2-axle truck, they did simulation studies. These two are simulation cases. The third one is from field experiment. So the numbers are presented in the error percentage. So the A1 is axle 1, A2 is axle 2, and GVW is gross vehicle weight. So even from field test, they were able to achieve only a small 2.7% error in the truck weight estimation. And we have generated quite a few conference and journal papers from this research. And since we're at the end of this project, and the water sensing device development is finished, we have quite a few road shows just lined up for this year. There's workshop on structural health monitoring and world conference on structural control monitoring, etc. Even at ASME Mechanical Engineering Conference, and we applied for student hardware competition in that conference. So the summary, we developed a multi-lateral new generation water sensing system, and system shows excellent performance with a large variety of different sensors. We've shown various non-destructive evaluation, ultrasonic energy, and our partner at Birmingham has achieved progress in the wind motion study. So next, we'll make, our plan is to make the multi-lateral water sensing unit system available for our research community in structural monitoring, distribute the hardware, distribute the software, so that anyone who is interested in building monitoring or bridge monitoring can have a chance of using our devices and our software, etc. And we are working with the GDOT and the Alabama DOT to identify bridges for field testing of those water sensing system. And our next excitement comes from this water drive-by inspection. So we'll instrument water sensors not only on the bridge, but also on the trucks. So in real time, as the truck drives through the bridge, we measure the bridge vibration, we can also measure the truck vibration. It gives us unprecedented data for analysts for studying vehicle-bridge interaction. With that, I'll stop here and be glad to take your questions.
Thank you. I think the presentation is very impressive. I like the technical content. But my concern typically is there's still a big gap between what we do in research and what is being applied in practice. Because I still don't believe the DOTs are buying the idea of structural health monitoring. I've been on several proposal teams that, it's okay, try it on one bridge and you pay for it. But we don't see it being applied everywhere like we would like it. I'm talking about like even since 15, 20 years ago.
Yes.
So how can we address this?
I think one of the biggest bottleneck of structural health monitoring on bridges is the cost. 20 years ago, people were dreaming about we're going to have thousands of sensors on bridges and buildings. Every one of them will be a few dollars each. That's not happening. That's not happening. We're still working on that. So the current system, the latest generation, we have tried our best to reduce the cost. Is still a few $100s. You want to do a large-scale instrumentation. If you want to have 50 or 100 those sensors on the bridge, it may not be affordable for an everyday bridge. So I think the cost is maybe one of the still the issues. But if you have important landmark bridge structures, then the cost may be less of an issue. So that's one side. The other side is really, like you said, is a research issue. Now we are able to get those tons of data. Then what do you do with the data? What does the data exactly mean to you? So once you get the data, can you just have an algorithm that directly converts the data to a bridge rating, 4 out of 10 or 6 out of 10? We're not there yet. So our civil structures are complicated, large-scale structures, and there's still a lot of research work to be done to achieve that goal.
Thank you.
Thank you.
I want to thank Dr. Wang. Thank you. All the speakers that asked the question. The session is open, please.
everyone. My name is Sahar from Florida International University, and I'm here to present my research on innovative modular high-performance lightweight decks for accelerated bridge construction. And actually, it's a cooperation between FIU, UCF, and UAB. My outlines is introduction, problem statement, research objective, work plan and methodology, result and discussion, and implementation technology transfer. Of over 605,000 bridges in the United States, about 12% of them are structurally deficient, and another 6% are functionally obsolete. There are major problems with the decks, and most of the time we need the replacement of the decks, or we need to retrofit them, or sometimes we need to widen them. There are some traditional construction methods, but they have major issues, like they're time-consuming, they're costly, and most of the time they result in major delays in traffic. What are our current needs? We need sometimes repairing the decks, we need sometimes replacing the decks, and we need sometimes widening them. And there are some challenges between these needs. For example, we have challenges with strength and serviceability. The self-weight of the deck is sometimes a problem. And of course, there's some problem with the cost, the construction time, and sort of things. One of the options for solving this problem is innovative modular bridge deck options for accelerated bridge construction. What we have investigated is a project with this Florida DOT. Actually, in this research, we look at alternatives to movable bridge decks, but now in UTC, we are going forward and change the project to general lightweight decks. But the alternatives that we investigated in that project were 4 alternatives. First one was the aluminum deck. The second one was using ultra-high performance concrete with 2 types of reinforcement, either with MMFX, which is kind of high strength steel, or FRP, which is another type of reinforcement that we use for this UHPC baffle decks. And the last section was the hybrid section of UHPC and FRP. Since the aluminum deck was provided with Sahar, so we have to deal with the casting and building the baffle decks of UHPC and the hybrid section. The methodology contains 5 steps. First of all, we have to do some literature review on what are the current status. And then we came up with the permanent design of the sections, especially for the baffle decks and the hybrid sections. And then through small-scale experimental tests, we calibrate our models. We have some issues between the behaviors of the UHPC and the HSS or FRP, or in the hybrid section, we have some problems with the FRP laminates and the UHPC. And then we run some tests on the component connections based on actual truck loading. And then we are going to calibrate our models and hand out some guidelines. We have actually two set of tests. For the first set of tests, which can be seen in the top right, we use a Sahar aluminum deck section. As can be seen in the graph, it's a sample output. As can be seen in the graph, the first set was too strong. The specimen was too strong. And the ultimate load that we captured through the experimental test was very larger than the required demand, which is the straight line. So we came up to this idea that we have to reduce the section. That's why we come up with this kind of section here. The difference between the new section, the optimized one, and the previous one is the deeper inclined element, and the difference between the variable top surface plates. This optimization happens because there were some failure in the bolt, failure in the connection, and through the uplift test or shear test, and of course they changes the types of the bolts that they use. The second section that we used were the UHPC baffle deck. For the first set of tests, we used the overall section height was 5 inches, and the number of the bar that we used was 7. So as can be seen in the graph, for the first 2 sets of tests, we came up with ultimate load of about 45 something, which is very higher than the proposed demand. So we reduced the sections as low as 4 inches of the height, and the longitudinal rebars became 5, MFX number 5. And as can be seen, the result shows that it's still a little upper than the demand, but we cannot go forward because there are some limitations for the height. The dominant mode of the failure were the shear cracks between the supporting girder and the loading pad. In order for us to monitor the continuity effect of the deck panels, we built several specimens on multiple spans, and in order for us to monitor the load distribution pattern, we cast and test multiple deck with single unit. The same process followed for UHPC with FRP reinforcement, but here we have to deal with the anchor systems. For the first set of tests, we use FRP laminates, which is impregnated in resin epoxy. Although as can be seen in the figure, although the results were promising well, but the slippage occurred. So we have to focus on different anchor systems. Then we came up with this kind of steel tube filled with kind of epoxy expansive grout, it's fair to say. And as can be seen in the second set of tests, we not only met the demands, but also the slippage did not occur. Besides that, multiple spans, multiple unit tests, we run some kind of punching through tests. As can be seen in the first set of tests for the FRP sections, the punching through happens in the first week. For the last specimen, we use the hybrid sections. For building and casting this specimen, we use kind of vacuum bagging systems. There were 6 specimens tested in this way. The difference between these specimens were the number of the layers of the laminate that we used, both in flexural and in shear. There were different kinds of things. And there were some differences between the thickness of the slab. They usually see a slab on the top. One of them were 3/4 inch, the rest were 1/2 inch. And as can be seen, the specimens were tested on the truck loading based on AASHTO in single span, single unit in the bed span. And unfortunately, there were problems in the shear off of the UHPC from the FRP side. The debonding result in failure mode here. As can be seen, we couldn't meet the required demand, but now we are focusing on how to solve this issue going forward. This technology can be transferred through different steps. First of all, the representative from DOT can take a look at this research, and of course they can think about the potential implementation in their states. Actually, advanced courses in bridges can be taught at FIU, UCF, or UAB, and we have an accelerated bridge construction center at FIU. This research can be presented there, and actually it can be presented in several journals or TRB annual meeting. We are handing out our proposed decks and guidelines. We are offering this to FHWA and DOT, and hopefully we are looking for infill application for it. Thank you, and I can take
Questions?
Did you look at any, for the aluminum bridge deck, well, not a whole lot of information on that. Did you look at the effect of, say, a sacrificial layer on top of the aluminum deck? I would be concerned about the effects of traffic on the aluminum deck, like maybe an inch and a half of asphalt or something like that that would provide additional dead load to the bridge. Did you look at anything like that?
Actually, in the second set of tests, which we are going to do in the next few months, we are looking at the top surface and the effects of the traffic on that. For sure, it needs replacement regularly, and that's why it's our first alternative. The rest are for UHPC kind of things, or for the hybrid section when you have UHPC at the end. The topping surface is not needed. That's why we are looking at aluminum deck for this issue in the next set of tests.
So I didn't hear you actually say, are you going to consider some kind of a sacrificial layer in addition to the aluminum deck?
Yes, there are a topping surface there, yeah.
All right, thank you.
Sure.
Thank you very much.
Good morning, I am Ghasemi, Ghasemi. This work is carried out by Mr. Vitali, Khaikine, myself, and Dr. Eric Shepard, the Dean of the school. And the work is on use of acoustic emission in non-destructive testing for the, the cracks in the bridges. Yeah, in this topic I am going to talk about the type of bridge we have selected for testing, then the kind of AE instrumentation adopted, some of the preliminary tests carried out in the past means a few months back, and then some of the current work which we have carried out just now. Yeah, the bridge is in Norfolk. It was suggested by VDOT, Virginia Transportation Department, and it is a bridge for Interstate 64. The bridge has got steel girders, and there are 10 steel girders, and the steel girders also involve the cross-link stiffeners, etc. They are all welded, and welding joint is prone to get fatigue crack in the heat affected zone, and heat affected zone, and this is a photograph of how we install the probes in the girders, and there was a place where we suspected presence of defect because it was clearly seen. There are 10 girders, and we have we concentrate on girder number 8 and girder number 9 for testing, and some of them had indicated as if it has got defect. For example, here we see a welding defect. Here we see a welding defect, it's arrow mark indicates. And we do not know whether the defect is detrimental or it can be forgotten. If the defect tip is sharp, then it is likely it will propagate with the time. Otherwise, it may not propagate, it may be harmless. And even though it is visible, it was not clear to VDOT whether they have to attend to correct it or not. We mounted 2 transducers to start with around that, and we started monitoring the signal. We started calculating the time of propagation each event gives rise to. And this is the instrumentation we used. We have used Misra's physical acoustics, Misra's sensor highway 2, which has got about 16 channels. And this is what we used. We used 150 kilohertz probes with the built-in amplifiers. And this is something about the acoustic emission. Acoustic emission signal comes out as a burst. Whenever there is a propagation takes place, it's going to give rise to signal. And each burst can be quantized by identifying one of these parameters indicated in the diagram, like rise time, peak amplitude, the duration of the pulse, etc. We have to set the minimum threshold level below which we will ignore the signal. In that way, we can avoid the ambient effect of ambient noise. And one of the characteristics of the acoustic emission and fatigue crack is when the fatigue crack is in the initial stages, the signal level is very small. And as the crack propagates, the signal becomes more and more stronger. We get more number of hits per time. And that is an indication whether the crack is harmful or not. And that was the kind of test we carried out a few months back, last June, July, September. And this is on the girder number 8. And in June we got some results. And if you see that, there's a very small increase in the activity. But it was not clear whether it is going to give rise to, it is going to show off any of the defects. We have not gone through full impact. There is a very small indication of activity, increase in activity with the time. And the amplitude increase, we were looking for amplitude and number of beats. All this is for another beam number 9, and all these plots were taken for a certain number of period time, for about 4 hours during same time period, 9 o'clock to 1 o'clock, so that the bridge is subjected to similar kind of loading. It involves both the busy time as well as light loading. And we do see in this beam number 9, in June, we do see the activity on the leftmost side, and this is in September. We could see a very clear increase in activity. Therefore, it is highly suspicious. There's a strong evidence for this to have a defect. Yeah, we have identified beam number 8 and beam number 9 are likely to have some defect, but beam number 9 appears to have very strong evidence that it has got defect. And we wanted to locate the defect and find the nature of defect. And we installed more number of transducers, 4 transducers we installed. That way we can locate the source of event. And also we wanted to carry out the test for a longer time. The previous equipment we had could work only for 4 hours. That was the life of the battery time. And we acquired another equipment which could be used for more than 2 days. And this we carried out on beam number 9. The left diagram was the result taken in September. The right diagram was carried out in January, February time period. The scale is not same. The scale is different. If you see, the activity has got increased 10 to 25 times in the period of about 5 months period, and suggesting that there is very likely that the defect is expanding, propagating. And conventionally, these are all carried out, the tests are carried out by VDOT people, the transportation people, by visual examination. It is very subjective, and due to human fatigue, they may fail to identify, notice some of the defects. But AE instrumentation, we thought of using it so that the test result can be automatically be projected to indicate what the defect is, where the defect is, etc. And since we have got these results, and VDOT is carrying out dye penetrant test in the suspected area to look for presence of hairline cracks. And this is again a comparison of what was detected in September and what is being seen now. And there is a quite considerable increase in the amplitude. This plot gives the location of the source or activity. The top diagram shows the linear plot. It shows the position of the transducer. There are 4 transducers, and we see transducer number 2 predominantly produces a lot of near probe number 2. We have a lot of excitation in that location. Activity is taking place in the space. And the bottom diagram shows the 2D plot, and it shows the distribution of the signal, and which is very close to the suspected area. And we also employs make use of students so that they get educated about the different NDT technique, and this is some of the tests they carried out in the lab on test samples. And to summarize, Department of Transportation in Virginia identified a bridge in Norfolk. We carried out a preliminary test to look for which of the turn girders may have possible defects. We identified girder number 9 to have predominantly stronger, giving stronger emissions, and we try to incorporate 4 transducers so that we will be able to find the location of the emission. And what is the use of carrying out these tests? Conventionally, visual examination is carried out by VDOT people, which they may, during that, in that test, they may miss identifying some of the defects, whereas automated AE testing will help in revealing the defects in appropriate time so that corrective measure can be carried out. And even though AE technique is more than 30 years old, it is not fully implemented in many of the bridges. Only critical bridges are focusing on using the AE technique, and we wanted to explore how reliable the AE technique is compared to conventional examination. That's one of the goal. And also we want to come up with a procedure technique to apply it more reliably. That's all. Thank you.
Questions?
Thanks for the talk. My question is with number 9, where you the AE sensor detected more
a higher probability of an active crack. So after that, is there any way to further confirm, either through visual inspection or through some other sensory instrumentation at that location through some other approach to confirm that
Yeah,
result?
actually we thought people are using dye penetrant test to see whether hairline crack is around that area. Yeah, we can use ultrasonics, etc., but it depends upon whether the geometry permits to carry out those tests. Of course, we can think of several other tests, but I see that VDOT people are using dye penetrant tests.
Dye penetrant is able to confirm that.
Yeah.
Thank you.
Do you see ultimately an ability to measure how fast cracks are propagating?
Yeah, we may have to carry out a lab test, and yeah, we have not thought of it, but it's a nice idea. I will see how we will be able to carry out by auxiliary measurements. Maybe like the resistivity method also can be used to see the change of resistance in that area. Maybe.
Hello, my name is Mohamed Gallow, a graduate research assistant at the University of Alabama at Birmingham. I'll be presenting today mitigating fatigue of cantilevered overhead sign structures due to truck-induced wind gusts and natural wind gusts. This research is sponsored by Alabama Department of Transportation and CTSPM. The principal investigator of this research is Dr. Fuad, and co-PI is Dr. Hosh. I'd like to express my gratitude for their effort during this study. Problem statement. There has been several cases reported all over the US for overhead cantilevered sign structures. Failures mainly because of fatigue vibration. Fatigue vibration are mainly caused by natural wind gusts, truck-induced wind gusts, vortex shedding, or galloping. We're concentrating in these studies on two factors, natural wind gusts and truck-induced wind gusts. An estimation about 20 cantilevered support structures were failing every year. This study came from a 7-year survey. This 7 years gathered around 100 failures. From unreported cases and doing the statistics, they found out this number. Okay? I'd like to give a background for fatigue. This graph is for bolts failing in fatigue. Fatigue is a degradation of material strength due to cyclic loading. It starts with the crack initiation at the lower side of the cross-section, and then as shown here is the cross-section. Then this crack starts to propagate. This propagation can be seen at the pinch marks in the cross-section until the cross-section couldn't sustain the load anymore. Then it suddenly fails, as shown in the upper part of the cross-section. Sustainability of overhead sign structures to fatigue vibration. Overhead sign structures are designed these days with smaller cross-section and lighter, which cause them to be more flexible and more susceptible to fatigue vibration. We have to deal with this problem by considering its vibration. Why is that? This came from the nature of wind gust. Wind gust doesn't have a specific velocity. Rather, it has velocity components that are oscillating over a large range of frequencies. That's why we need to consider the randomness of wind gusts. We use that by using a spectrum velocity, power spectrum density for velocity of the wind. As shown in this graph, the value of this velocity peak around the frequency of the wind of 0.01 hertz. That's why we need the structure to be far away from this frequency, because the resonance occurs when natural frequency of the structure matches the frequency of the wind. And we know that wind has a lot of frequencies. That's why we need to shift this resonance to higher frequencies. That's why we need the structure to be more to this side. Cantilevered overhead side structure align between 1 to 3 hertz. We need to increase this number. The objective of this research is mitigating fatigue stresses due to natural wind gusts and truck-induced wind gusts for cantilevered overhead side structures. To achieve this objective, there has been an approach. As we know, frequency is dependent on the mass of the structure and its stiffness. As mass decreases, frequency increases, and the opposite for stiffness. Stiffness is remarked as K in here, and mass is M. We are going to consider 3 points. The first point, we are going to fulfill all ASH2 specification requirements for design and use practical member shapes, such as rectangular, squares, or circular. And the last thing, design economy. It was expressed by the weight of the structure. The lighter is the better, even though it makes the structure more flexible, but we're looking at stiffness of the structure. The work plan. The first thing we needed to do is assembling shop drawing, different ideas of cantilevered overhead side structures. I used 3 layouts for this type of structure. The first one is 4-chord, then 2-chord mast arm, and the third is monotube. After that, we need to find the loading function or the excitation function for these structures. We're going to consider natural wind gusts loading function and truck-induced wind gust loading function. Then, a full-scale 3D modeling has been performed on a finite element analysis software. I used SAP 2000. From this analysis, I calculated the frequencies of the structure. And for checking its accuracy, I compared it with experimental field data. I modeled one structure that has already been in the field, then made some modification structure so that the eventual frequency will match the frequency of the model. Then I calculated, I got its responses, which was represented in fatigue forces at critical section of the structures. Most of the structures are failing, cantilever structure are failing at connections near the base of the post, the base of the connection to the ground, and the connection between the mast arm and the horizontal post. I was concerned in this study to calculate forces at the base to represent fatigue performance of the structure, the whole picture of it. Then I tried to investigate different factors that are affecting these fatigue stresses. The factors that I studied are member sizes, member shape, and truss member arrangement, and eventually structure type. I used the last one for the last comparison for structure, because each structure has different cases and different variables. Eventually, I made the conclusion, which is the best structure, and then, of course, the final report will be presented to include all the outcomes of all the details of the study and outcomes. Structure excitation. On the velocity power spectrum density that I showed earlier, I deduced the wind pressure power spectrum density. I entered the loading function on the finite element analysis to represent the wind, natural wind, and for truck-induced, I used a time history loading function. I used a 70 mile per hour truck speed because this is the maximum speed in the state of Alabama. I did a pilot study on these loads. I designed a very simple cantilever column and then loaded it with these functions in order to get a relation between the structure frequency and its response for fatigue stresses. These are the curves that I got. These are equivalent static loads that has the same, or that cause the same dynamic effect of dynamic loads. Okay? As we see here, the frequency between 1 and 3, which is in this zone, this is where cantilevered side structure. This is the slope in here. If you magnify this zone, it will be a steep slope. You can see a steep slope. Specifications determine a constant limit or a constant value for this load. Yet in actual life, there is a difference. As frequency increases, these loads decrease. And for truck-induced wind gusts, the frequency between 1 and 3 is in this zone. We need to shift away from the peak. The peak is around 1.7 hertz. either increasing or decreasing, okay? Each structure has its footprint. How is that? There are several frequencies for each structure. They are sorted from the lowest to the highest. The first frequency is for a mode of vibration that the structure has the least stiffness to resist this type of motion, or this mode of motion. That's why we're concerned about this, because if the structure has low stiffness to this type of motion, this means that it will experience larger deformations. Larger deformations for the same materials mean larger stresses, which mean larger fatigue stresses. And this shortens the fatigue surface life of the structure. That's why we are interested in investigating the initial response, initial modes of vibration. Another point, we're interested on the mode of vibration that is causing the structure to move in the same direction of loading, because this is the worst case. For natural wind gust, the load is acting horizontally on the side, which is causing it to move this way. This is the first mode of vibration. It has the lowest frequency. The frequencies that I got from finite analysis was 1.53. From the field experience was 1.61. This is for the same structure. The difference were consistent. It was around 5%. Fatigue stresses were 5.28. As for truck-induced wind gusts, as the truck passes beneath the sign, it starts to vibrate. The load is acting in two directions: horizontally, which is minor, and vertically, which is a major load. I neglected the horizontal because it's already considered on the horizontal wind gust, natural wind gust, and it has much larger value than this. The vertical is only considered in here. The mode of vibration of the deflection caused by this motion is like this. This is the second mode of vibration. It has the second lowest frequency. These two modes of vibration are controlling the dynamic response of the structure to dynamic loads or wind loads. Fatigue stresses I got the same frequency for second mode of vibration. Fatigue stresses for truck-induced wind gust was 0.306. Yet for natural wind gust, it was 5.28. So it was a very large difference. That's why when designing, according to considering fatigue, I'm more concerned about natural wind gust. Truck-induced wind gust for this type of structure will not cause failure, but rather natural wind gusts. However, for VMS sign structures or variable mass signs, it has larger cross-section from the downside, which means larger area exposed to wind pressure due to trucks. This is our concern. But here we're considering normal sign structures. First structure that I considered investigating in this study was four-core cantilever sign structure. It was broken down structurally into these elements. The first one is a post, and then truss or mast arm members, horizontal arm members, cords, vertical truss member, and diagonal truss members. This is the pole, the reinforced concrete pole, and this is connected, and this is the sign. I'm concerned about the pole, the post, and cord members. These are elements I'm going to play with to improve the structure dynamic performance. Second structure was two-cord cantilevered overhead sign structure. It was broken down into same thing: cords, vertical truss members, diagonal truss members, and of course post. Now, before going to the third type, I'd like first to discuss the factors that are affecting these type of structures. First, members shape. I considered these shapes and combinations between them. I know that elliptical is not a practical cross-section, but out of curiosity, I wanted to investigate it to see its effect. Maybe if it caused a large effect, I would maybe consider it in designing or manufacturing these type of structure. I found out that for mast arm members, changing the member size is not significant. However, for the post, it was different case. Every change in the post, even if it was very little, is going to affect the dynamic response of the structure or fatigue stresses. How about member size? The same here. If I increase member sizes for the post, it will be more significant than mast arm. There's one thing about mast arm members. If I increase the size of mast arm members, I know I will increase its stiffness, but there is another factor in the equation, increasing its mass. The mass effect on the structure frequency was found to have larger impact than its stiffness itself for the mast arm. That's why I have two sides, mass stiffness of the mass arm. I increase the mass, increase the frequency. Increase the stiffness, I increase the frequency. Increase the mass, lowering the frequency. The mass has a larger impact, so the end result will be decreasing the frequency, which I don't want that. I want increasing the frequency of the structure. The pulse was different. Its stiffness has a larger effect. When I increase the stiffness of the pulse, I found out that fatigue stresses are dropping. This is the curve that represent the size of the pulse and fatigue stresses. I pictured the size of the pulse at the ratio between its diameter to thickness. Because one might say, I might just increase the diameter of the pulse. Well, you can increase it to finite, infinite limit. I'm interested on this ratio to get economic design while obtaining remaining the integrity of the structure and improving its dynamic performance. Third thing was members arrangement. As you saw, truss members, I can play with the members arrangement, vertical truss members or diagonal truss members. I can use Warren truss with verticals, Varendale truss, diagonals in tension, diagonals compression. All of that will not have significant effect. Even the spaces between chords, I use the range between 3 and 4. I used 3 feet, 3.5 feet, and 4 feet. I didn't have significant effect. This tells us that the stiffness of the mass arm is not as significant as the stiffness of the post. Because changing all these members, what I'm looking at, as I said, stiffness and mass distribution. Now the third type is a monotube. I use three layouts for this structure. First one with a slanted post with curved end. Slanted post, I use an inclination of 10 degrees. And here, for all these type of structure, the field splice is located between the horizontal arm and the starting of the curve. And in here, in this case, it was located on the meeting point between the horizontal member and the vertical member. Okay. The second case was vertical post with curved end, and the third was both are straight members. The post was vertical in the third case. Factors that are affecting the monotube. The first thing, the layout. Frequencies of these layouts, I found that the first one has the highest frequency, and then decreasing for the second and even more for the third. However, when I calculated fatigue stresses, it was almost the same. Why is that? It's supposed to be the least value in this. The reason, this is a preliminary study to see if at first to get a picture which one is the best. From here, I got the same or very near values because I used same cross-section, even from mass arm members. But this is not the case. I had to redesign the model because when I shifted the field splice closer to the sign, this means smaller design of the mass arm, which means less mass, which means higher frequency. So I started to know that the first case is a better, but I needed a strong motivation to consider it as a best. The second thing was considering fatigue stresses at field splice. As I said, critical cross-section for fatigue are located at main connections. Connection at the post base and connection between the horizontal arm and the post. That's why I looked at these stresses. For the first case, it was 2.4 KSI, the second 2.92, and the third was 4.6. This one, I concluded that it's the best between them. Second factor is the radius of the post. It's the gear itself. I used 3 radiuses, 8, 10, and 12 feet. By the way, these values I got from Alaska Department of Transportation standard specification of Alaska Department of Transportation from their drawings. I did the calculations. For each radius, I redesigned the model. As you see here, for this, I used radius of 10 feet. Okay? This is fatigue stresses for 3 cases. I found that the least one is for R12. And the same here, when I increase the radius of the curvature, I shift the field splice closer to the sign, which reduces the susceptibility of connection to fatigue stresses. It's 4.87 KSI at this location. It's higher than this one because in here I redesigned the section and I got a smaller cross section. That's why it's within the limits of, it was larger than this value. Okay, third factor was member sizes. The same in monotubes was as 2-chord and 4-chord sign structures. I found out that post is the most controlling one. But in monotube, it's a different case. For consistency in design, I use same diameter for post and mast arm. I was interested in the connection between them. I had to use the same diameter. The only difference between both designs was the wall thickness. For the arm, it was definitely smaller than the post because it has lower stresses. The design was based on maximum loads. Dead loads, the weight of the structure, and maximum weight according to 100 miles per hour point speed. As that D over T for the post was increasing, the frequency of the structure was increasing as well. And for that, fatigue stresses were reducing. And here, the middle line representing the weight of the structure. I found out that the structure's weight is not changing significantly, which means that if I increase it, it's okay. It's still economical and will be better for fatigue performance. I found out also from the ultimate design, or maximum load design according to only weight and maximum wind loads, that the optimal cross-section is obtained at ratio B or T 1.05 to 1.1 of the compact limit at this value in here in the middle. If you increase the larger scale, instead of 0 to 7, let's say 2 to 4, you'll find the curve goes like that. This is the most economical section for the cross-section area. For this value of D over T. Now comparing the three layouts, which is the last factor of controlling fatigue stresses or mitigating fatigue stress. First one is 2-chord, then 4-chord, and monotube. These are comparative with weight of structure. First one was 4.9, the monotube. And then the 4-chord was 5.4. And eventually the 2-chord was 6.3. This is a large difference in weight. It was 0.9 to 1 to around 1.1 and 1.2. And as for frequency, this one has the highest frequency. And then frequency decreases in this direction. So this one might say that it is the best. But when I calculated fatigue stresses, I found something interesting. This is due to natural wind gust. I found out that for monotube and 4-chord, stresses were almost the same. However, it was larger for monotube. Why is that? Because I have higher stiffness. This was because stresses, the exposed area to wind due to the stocky cross-section of the monotube caused higher stresses. But they were almost the same. As for the last one, it has the highest fatigue stresses because of two reasons. It's low frequency, and the second reason is the high exposed area to wind. I have two stocky members. This graph just for convenience. This is for truck-induced wind gust. As you see here, I said that 1.7 hertz is the peak response at 1.7 hertz. The first structure, even though it has lower frequency than the others, yet it was shifted away from this value. That's why I got the least fatigue stresses. The conclusion, critical section of fatigue, was based on the literature review, was located at critical connections, the connection between post and horizontal arm and the base of the post. Second thing, fatigue stresses due to truck-induced wind gust is not as significant as natural wind gusts. Increasing structure frequencies reduces fatigue stresses. Changing the stiffness of the mast arm is not as significant as changing the stiffness of the post. And as we said, as we increase the E over T for the post, we decrease fatigue stresses related at its speed. And I concluded that the best structure was the monotube, slightly monotube size structure. It was the first one, the last one, sorry. And different truss confirmation, of course, we said that it doesn't have this effect as the post, and even its distance is really important. Thank you. That sums up my presentation. If any one of you have any questions, I'm ready to take.
Yeah, my question is, you analyze the individual factors for the design of your cantilever designs, and then you try to combine all of that factors together to see which are the best.
Yeah, for each structure I did that.
Yeah.
However, it's very difficult to combine different structures because they have different criteria. For instance, I cannot control or get the factor of truss members arrangement for the monotube because I don't have truss members.
Okay.
See? For member sizes, I concluded the best cross-section first, then for this shape, sorry, the best shape. For this shape, I changed the size of this shape for all members.
Okay.
And these are the best combinations.
Okay, I think the reason why I'm asking this is those factors that you analyze that are independent. If they are not, probably it's better to combine them.
I did combine them.
Okay.
The table for a member shape, I did every combination. I did over 100
Oh, okay.
models to include all of that.
Thank you.
Yeah, thank you. Any question, please? Any more question?
We want to thank all of our speakers. A bit of our logistical information. Lunch will be at 11:30 at the Georgia Tech ballroom, and the panel discussion will start at noon. Thank you so much for your attendance.
You were there last year. Okay, that's good. You weren't there, I guess.